So we've already seen the definition of a permutation. It is an arrangement of objects in a specific order, and that order is important. And this will become even more important because later on we'll learn how to do arrangements of objects when order isn't important, and that's called a combination. So right now, permutations, the main thing is order is important. And the first one, if you had to write all the permutations of A, B, C, well, this is one of them, and this is another one. Oops, did that one already. We could write them all out. I know that there's going to be 6 of them because if I do my spaces, how many choices do I have for my first letter? 3, then 2, then 1. And with permutations where you are using a set of objects and arranging them, the idea is that once an object is used, it's not used again. So we don't have with ABC, AAA, or BBB, or CCC. And with permutations with objects, we've also learned that we can show that with our factorial notation. So 3 factorial. We've seen the permutation formula already, NPR. And here are some interesting examples. If you have n objects, and you're arranging all n of them, that's just n factorial. And you'll notice, remember when I said sometimes 0 factorial appears in a definition in order for it to work? And by definition, 0 factorial is 1. So this is one place where that shows up. If you had 3 things and you wanted to arrange all 3 of them, well, that's like 3 spaces starting with 3, 3, 2, 1. That's equal to 6. But according to the formula, this would be 3 factorial over 3 minus 3 factorial, which is 3 factorial over 0 factorial. And the only way this is equal to 6 is if the bottom is 1. So that's part of why we defined 0 factorial to be 1. Yeah, 0 factorial is 1 just by definition, so that when you're working with these situations where the formula gets a 0 in it, it only makes sense if it works out to be 1. So that's why it's defined that way. So for the most part, we do spaces. But if you wanted to, you could use the formula. But I find with these questions, here we have the wind ensemble has 10 pieces, and they're going to play 4 pieces. And the order matters, because it's kind of weird when you play O Canada as the 3rd song of a concert. People are like, oh. But it could happen. How many ways could this be done? Well, you have 4 decisions to make. What's going to be our first piece, our second piece, our third piece, our fourth piece? And I would have 10 choices for my first one, 9 for my second, 8, and then 7. But this could also be written as 10p4. So sometimes you'll see in multiple choice questions, they'll have this question, but the multiple choice answer will be 10p4. So although we'll normally use the spaces to figure this out, it's important to know, oh yeah, that means the same thing as 10p4. So I'm able to work with both of those situations. If you rearrange the letters of the word math, well, we could do 4 spaces, 4, then 3, then 2, then 1. But this one might be one that you can just directly say all 4 letters are different. I can just do 4 factorial. I find that this is the hardest permutation problem because 5 people come for math help and there are 12 desks. How many ways can this be done? This is hard because people, when they're trying to make their decisions, they want to draw 12 spaces because it's quite easy to put a student into a desk. And so you want to draw 12 spaces for the 12 desks. But we only have 5 decisions to be made here instead of 12 decisions. And you're actually, each student makes a decision, and then the desks go into the students. So it's kind of opposite of what your mind might think, but how many choices does that first student have when they come in? They have 12 choices because they could pick any of the desks. Then the next person, right, because most people, it would be a little awkward if you came into math help and there was 12 desks and you were sitting in one of them and the next student decides to come in and sit on your lap. It'd be a little awkward, I think. So that's why there's 11 choices, then 10, then 9, then 8. Or we could write this as 12p5. So now if we look at our class today, right, we've only got a week and a half left of December, and then there's a new seating plan in January. How many people are here right now? If we just use the people that are here, 5, 10, 15, 20, 25 people, and there's 30 desks. So if we wanted to figure out how many seating plans are possible here, we have 25 decisions, right? It's going to be 30p25. And if we type that into our calculator, right, I should have it as a bonus on the next test. Guess the next seating plan. If you guess right, you get 100% in the course. Has anyone done the number?
Yes.
It's too many. Oh my goodness. Yours actually tells all the numbers there and lets me scroll forever.
Yeah.
Wow. Let me write it out because it's just fascinating. Are you ready? So, if I said I'm going to randomly do it, 25 people, 30 desks, so you have to even predict where the empty desks are going to be. And if you get it right, you get 100% in the course. Your chances are 1 in, here we go, 2, 2, 1, 0, 4, 4, 0, 4, 9, 8, 4, 3, 4, 9, 2, 5, 4, 8, 8, 6, 3, 5, 9, 0. Just a second. 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. There we go. Pretty good. Pretty likely that you'll get this, right? No. So I could do this year after year after year and never have to give out the 100%. Now, there is the slight possibility someone could get that right. I mean, if someone were to guess this many times, which is quite a lot, 3, 6, 9, 12, 15, 18, 21, 24, 27. This is roughly 22 octillion, if you want to know how you would read that number. Roughly 22 octillion. Chances are I'll never have to give out 100%. If they took the class that many times in their lifetime, I would hope they would pass. But yes, then there is a possibility. And that's the idea, again, remember how I talked about that? Did I talk to you guys about the pigeonhole principle? Yeah. So with lotteries, lotteries are set up this way, that they're very, very unlikely to win. And we're going to look at some lotteries and what are our chances of winning in this course when we do combinations. Because Lotto 649, you just pick 6 numbers from 49, but you don't have to get the order right. So it's not a permutations question, it's a combination question. It would be much harder if you had to get the order right, but you just have to pick the right numbers. And the chances are not very good, but eventually, so many people play because the prize money is so big that more tickets are bought than numbers available. So then there is a good chance that someone wins. However, with that, some people can buy the same ticket. So in order to guarantee that you would get this right, you would only have to, write out 22 octillion different seating plans. And that shouldn't take you very long. Now, we're going to change this title. So you can just stroke that out if you want, just so that it matches the notes that we did earlier. We're going to change that part to permutations with identical objects. These were our Mississippi questions that we looked at earlier. So this is review. If you had to do egg or Assissippi, how would you do that? Well, egg would normally be 3 factorial, but what do we do with the double G? We divide by 2 factorial. So there's only 3 permutations of egg. Assissippi would normally be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial, but what are we going to do with the 3 S's? Divide by 3 factorial. We also have 2 I's and 2 P's. We don't have to worry about the A or the E because there's just one of them. And we've seen that these kind of questions can come up in different ways. So here's a contractor is selling model homes of type A, B, and C on a street. She sold 3 of model A, 4 of model B, and 2 of model C. So now they have to decide how they want to build those on that street. Well, again, if you can represent things with letters, then you can think of it as a Mississippi question. Now, how many letters do we have? 9. That would normally be 9 factorial if all the houses were different, but we have to divide by 3 factorial, 4 factorial, 2 factorial. You ever driven through a newer development area? Does it feel like they have like 4 or 5 different models and it's just sort of like, yeah, that one's the same as that one is the same as that one? It's not until you go into an older area that like every house is kind of different. But even then, sometimes you find out all of those houses were built in the 1950s and there was still only 4 models in the 1950s. So you see houses that are the same. And here's our Graham question from before. John lives 3 blocks north and 6 blocks east of school. All right. So there's 3 blocks north. What corner will I put John? What corner will I put school? Not that it really matters, but John here? So John lives here? No? Now we're saying top right? School's going to be down here? Excellent. He wants to walk home, so he's starting here. He needs to go north 3 times and east 6 times. Ooh, this is like a Monty Python word. Okay, how many people have seen Monty Python and the Holy Grail? Yes, okay. The knights that go knee. There we go. That's how you spell it. Normally this would be 9 factorial if they were all different, but we divide by 6 factorial and 3 factorial to figure this out. And do you remember that we could also do this by the counting method? Any of those straight paths will be 1. How do I figure out this number? Add those 2, so this will be 2, this will be 3, this will be 4. 3, 4, 5, 6, 7. This will be 6. 4 and 6 is 10, 15, 21, 28, and then 10, 20, 35, 56, and 84. Nice. And these are very pretty numbers, but you don't know why they're pretty yet. I'll tell you why they're pretty later. Nope. So wait like at least a week. I know. Okay. That is where we are. Well, should we do grouping? Yeah, let's do grouping. So up till now, in the new notes, in the first section, we learned about dealing with restrictions first. That was a little bit new. We are now going to learn another new strategy, which is the grouping strategy. Sometimes you want to arrange things in a row, but you still want certain things together. Maybe you have a collection of DVDs at home, and you want to put them nicely on a shelf, but you kind of want your action movies together, and then your dramas together, and then all of your favorite cartoons from when you were younger together. So you want to arrange them, but you want to keep them in their different groups. So how do we do that? Well, we first arrange all the groups. So that's the first thing, is how many groups do we have? And if I have 5 groups or 3 groups, how many ways could I arrange 3 groups? That would be 3 factorial. And then you look at how many things you have in each group and multiply by that factorial for each one. So if you had 6 action movies, they could be arranged in 6 factorial ways. If you had 7 dramas, they would be 7 factorial ways. And if you had 52 kids movies still, that could be arranged in 52 factorial ways. So here's an example that looks at that. My collection of math books, right? I've got 4 calculus books, 5 algebra books, and 4 geometry books. And I want to keep those together. And we're assuming that these are all different. Okay? So 4 different calculus books, 5 different algebra books, 4 different geometry books. I want them in the shelf, but I want the subject areas together. Well, first, I would do 3 factorial, and I would, underneath this, I would do a little explanation that that's my number, how many groups that I have. I have 3 groups. Then I would multiply by 4 factorial, because that's my calculus books, 5 factorial for my algebra books, and then another 4 factorial for my geometry books. Basically, it's kind of like a fundamental counting principle. We have 4 main decisions to make. My first decision is, how do I want my groups? Do I want calculus, algebra, geo? Or do I want geo first and then algebra? Or maybe I'm alphabetical, so I want my algebra first, then my calculus, then my, right? So that's what I have to decide first. That's my first decision. And then once I've made that decision, then I've got to arrange each of my groups individually, so they're each a decision as well. Multiply this all out, and we get a big number. Example 2. You've got 5 people sitting on a park bench, and now Jill and Bill want to sit together. Ooh. So it becomes a grouping question because you want 2 people grouped together. Now, when you're thinking about this, either some people like to think of it as they're glued together and you think of them as a single person. Okay? In this case, you would have 4 people because there's Amy, there's Lee, there's Tom, and there's the Jill Bill that are always together. Right? And you guys know there's certain couples in high school, they like, are they ever apart? And you name them together eventually. We had 2 people that were this way. Her name was Carrie, his name was Derek. We just called them Carrick because they were always together. So we've got the Jill Bill as one person, and 4 other people. So we could think of them as 4 people. How many ways could you arrange 4 people in a row? That would be 4 factorial. And then you would have to multiply by 2 factorial, because the Jill Bill monster might be Jill Bill or Bill Jill, right? Now, if we think of them as groups, Jill Bill is one group, and each of the other individuals are separate groups. So we could call the 4 factorial our number of groups. Wow, if you could spell groups. Number of groups. Number of groups. And the 2 factorial is because it's Jill Bill or Bill Jill, because that's the number in that group. So part B. Poor Tom. Now, Jill and Bill, don't worry, Tom gets his revenge in part C. Okay, we'll get there. Jill and Bill have to sit together, and Lee and Amy want to sit together. So now we have 2 groups of 2 and Tom all by himself. So our number of groups is 3 factorial. Right? Because we've got Jill and Bill, Lee and Amy, and Tom as our 3rd group. Then we multiply by the permutations in each group. Well, the first group, Jill and Bill, that's 2 factorial. Our second group, Lee and Amy, that's another 2 factorial. If you wanted to put Tom in there so he doesn't quite feel so left out, you could put a 1 factorial there for that group, but you don't need that because there's only 1 in that group. And so originally we had 4 factorial, 48 ways with Jill and Bill together. And now with Lee and Amy together, we've got 6 times 2 times 2, 24 ways. And then we get to part C, which is called Tom's Revenge. And something happens, and now Jill and Bill must not sit together. Okay, we're not going to worry about Lee and Amy. They're sort of on again, off again, so they could sit together or not, doesn't matter. But we must make sure that Jill and Bill are not together. And I talked about this earlier. This is where we're going to have to use what I call the not strategy. It's not easy to count Jill and Bill separate, but it is easy to count them together. In fact, we counted it in A. Jill and Bill together in A was 48 ways. Counting all the ways is easy because 5 people with no order whatsoever would be just 5 factorial, which is 120. And the not strategy says if you can count the bad ways where Jill and Bill are together and you can count all of the ways, then you can just subtract them. And so 120 minus 48, there will be 72 ways where they're not sitting together. Right? So that was, you can imagine whatever you would like happened there, but they could not. I don't know why they still all went to the same park bench so many times. But, okay. So that is where we are going to end. We will leave permutations with cases for Thursday.